last class we stopped, I think we stopped right at the linear elastic fracture mechanics. Here we will continue from this point onward. Okay. Before I start, just one moment, I have to connect my iPad. It's recording. Okay. Okay. So I had just posted a poll on the exam timings, and most of you have voted for 3 to 5. Is this timing okay, or because since you will be fasting and you need to break your fast maybe around 6 some time, some of you may have a problem if it is between 3 to 5. Are you guys listening to me?
Yes, doctor.
Yeah. So 3 to 5, at least 1 or 2 students had a problem because I think they are far away from the university, and they claim that because of that, they will be too late for breaking the fast. Is it possible to have between 2 to 4? Anybody has a problem
Yes,
between 2 to?
doctor, no problem.
No problem, because 2 to 4 will be little bit better, because you guys can go early and break your fast also. So I think I will discuss with the other class also. Better to have between 2 to 4. Anybody has classes during this time, 2 to 4? If you do not have any classes, I will try to fix it at this time. I will also ask the other section. Let's say if they have a class, in that case, it is better to go between in the morning times. Okay, so let me discuss with the other class as well, and then I will inform you guys before next class. Okay, so let's continue from last class. So last class we went through, if you recall, we went through the strain life method, and we stopped right at this point, linear elastic fracture mechanics for fatigue loading. So let's see here. So we had 3 types of methods: stress life method, strain life method, and linear elastic fracture mechanics to predict the life of the part. We went through the experiments that we conduct for stress life method and strain life method, and we also saw some equations, the relationship between empirical relationship between the strain, total strain, plastic strain, and an elastic strain versus the number of cycles to failure. So it was an empirical relationship obtained from your experimental results. Now we will go through linear elastic fracture mechanics. So this is lecture 19. And let's type it in here. Okay. Okay. So what are the equations we are going to use in linear elastic fracture mechanics for dynamic load? Again, we will use the same equation. If you recall, Ki is equal to beta sigma root pi a. We are going to find the same stress intensity factor, but the maximum and the minimum value of the based upon the maximum nominal stress and the minimum nominal stress, we will get two Ki values, and then we are going to take the difference between them. Just like we had the definition of sigma amplitude, in the same way, we are going to calculate delta Ki in this case. Delta Ki will be the difference between the Ki values depending upon the sigma value, sigma A value here. Okay, so we assume stage 1 fatigue has occurred in linear elastic fracture mechanics. We assume stage 1 has occurred, predicts crack growth in stage 2 with respect to stress intensity. So in stage 2, the life of the specimen is found out. As long as stage 2 persists, life is there, and when it reaches the stage 3, we have the ultimate fracture, brittle fracture to be more accurate, and it is catastrophic fracture. When Ki reaches KIC value, then brittle fracture takes place. In the same way, we have to get a relationship. So let's see the equations. So the stress intensity factor is defined in this way. Using the sigma max and the sigma minimum values, we obtain delta Ki, and we get that. Testing specimens at various levels of delta sigma provide plots of crack length versus stress cycles. Okay. So what kind of experiment we do? We again do experiment with a lot of specimens and for various values of delta sigma. So in this order, we calculate or we do the experiments and then we obtain the data. Okay, so let's see here for various values of delta sigma value. Okay, we provide crack length versus stress cycles plot. Okay, once we have this plot, this is a different plot again. So we have this plot for various delta sigma values. Maybe on the y-axis we have crack length versus delta sigma. Okay, so from log plot of crack growth, dA or dN shows all three stages of growth. So from here, this plot, from the plot provided here, we will be able to extract more data. So let's assume we have a curve like this, and in this plot we can okay, so let's see here, we have several plots. Maybe we will be able to obtain what is the change in crack length for each delta sigma values. Okay, for each of the delta sigma values, we can obtain the change in crack length and how many cycles it took for failure. So finally, from this plot, we will be able to extract data between log delta K and log dA over dN. Okay, So somehow they extract this data and finally they plot this data over here. Now on the y-axis, what you have is the rate of growth of crack length with the number of cycles. On the x-axis, you have delta k value, which is this particular value. Now what you observe here is there are three stages in which the crack grows. Initially, the rate of growth of crack is very high at region 1, and then it flattens out, become a constant rate of crack growth in stage 2, and finally we have again exponential increase in the crack growth and then fracture. So the life of the specimen is decided between this range. Okay, so now based upon this graph, since this is a constant slope line, we can obtain an empirical relationship between dA over dN and delta K. And the empirical relationship, based upon the log plots, we can get two constants. One is the exponent, one is the constant value, connecting your rate of growth of crack length to your delta K values. Okay, so this gives you an equation which is called as the Paris equation. So finally, you will be using this particular equation for solving problems. So how do I find what is the number of cycles to failure, or what is the life of the specimen from this equation by rewriting this equation and then integrating the equation. So we can rewrite dA over dN as C times delta Ki to the power m. Take dN to one side and take all the other terms to the other side. To the power m, and then 0 to number of cycles to failure will give you what is the number of cycles to failure. And here will be the initial crack length, since we are integrating with respect to crack length, initial crack length to final or maybe critical crack length. If you know what is the critical crack length, then we can integrate up till the critical crack length, and the life of the specimen will be decided by that. Now the values of C and M are usually given in the problem. C has these values for steels given here according to empirical graph which was extracted, and M values are also given here. You have both in SI units and English units. So in your typical problem, these values will be given, and we will use this integral form of the equation then to evaluate what is the number of cycles to failure. So let's see an example problem. Here you have a bar which is subjected to a repeated moment, cyclic moment from 0 to 1200 pound force inch. The bar is made out of the steel material, ASI 4430 steel. SUT value is given, SY, KIC values are given. Material tests on various specimens of this material with identical heat treatment indicate worst case constants of C and M. C and M values are also given to be used in the Paris equation. A nick of size. So this is the initial size of the crack. AI is equal to 0.004 inches, was discovered probably by any non-destructive testing methods. And you're asked to estimate the number of cycles to failure for the cross section given here. Okay, so we do not have any change in area, so there is no stress concentration effects. As usual, we can evaluate the sigma values and then delta sigma values. The M values vary between 0 to 1200 pounds. So let's go here. The delta m value we can easily calculate. Here it will be maximum minus minimum. So that's the value we are going to use in the calculation of delta sigma as well. Delta sigma will be delta m over I times C. So delta m is 1200. The I for the cross section is 1/4 and 1/2 in the height. So BH cube over 12 and multiplied by half the length of this guy, 1/2 of 1/2, and we can basically cancel off these two, and here we can simplify further. Rather, we can calculate the values directly. Let's hold on a second until this opens so that we can calculate. We have 12 times 1200. We have a huge value. Let's see. So this is also in the denominator. Everything will go to the numerator, 8 times 12 times 1200. Let's convert that into kpsi and therefore divide by 1000. Let's see, here we are calculating kpsi. Let's also see the properties are given in kpsi. Okay, so that's okay. The value 115.2 kpsi. Delta ki is going to be beta. We will have delta sigma root pi. Yeah. Okay, so let's just use the beta value they have used in the slide. Let's see here if they use a particular beta value. Initially, they are taking the beta value to be 1. And let's see here. We're using the KIC value. Okay. So before that. So this is the delta Ki value we are supposed to calculate, but what is the A value to be used? So first, the question, if you read the question, let's go back to the question, what you are asked to calculate, estimate the number of cycles to failure, which means I need to use a particular formula for number of cycles to failure. A initial to A final, and then have the formula here. After substituting all the constants, we have 1 over C outside. Again, what they have done is they have substituted for delta Ki. 1 over C is a constant, so we can take it outside and rewrite the equation dA over beta delta sigma root pi A raised to the power m. Okay. We calculated delta sigma here. Now, if you see pi A, root pi A is inside the integral, and we are integrating with respect to with respect to A. So we need to find AI and AF. AI value is already given in the problem. The initial length is given to be 0.004 inches. So I can put the value here, but we do not know what is the AF value, final crack length. So how do I find the critical crack length or the final crack length? We can say critical can be found when your Ki is equal to KIC value. Now recall that your maximum is also equal to 1200, so sigma max should also be equal to 1200. Sigma max should also be equal to delta sigma value here, 115.2 kpsi. So we can write sigma critical or sigma, let's just write sigma critical value will be equal to 115.2 kpsi. Okay, let's see here. That's the value we have found. So for this critical length, let's assume initially beta equal to 1, because we do not know what is the critical crack length, and we will not be able to figure out beta easily. Again, for beta, if you recall, we have to go to the previous chapter, and let's see here. Let's take a look at the graphs on the edge crack. So this is the crack. To find the beta value, we need the A value at the critical crack length. We do not have the A value at the critical crack length, so we cannot get the beta value from this graph. So this is why we assume beta equal to 1 initially, and then we proceed with the calculations. Assume beta equal to 1. Go here, Ki will be beta times sigma critical, 115.2, or the so why did we assume sigma max is equal to sigma critical? If you think about it, we want at the maximum stress, what would be the critical crack length? Okay, so that we can calculate this number of cycles to failure. The final crack length should also be equal to critical crack length. Up till critical crack length, we want to find number of cycles to failure. So at max stress, we most probably we want to calculate what is the critical length when it reaches that point. Okay, so that at that point Ki with the sigma max value should be equal to KIC. So Ki is equal to, again recall, Ki is equal to beta times sigma root pi A. We are going to use the same formula here. Beta equal to 1, root pi times A critical should be equal to KIC value. What is the KIC value? It's given in the problem, 73 kpsi inch, 73. So that gives us directly what is the AC value. AC will be 1 by pi 73 over 115.2 the whole square, because we have to square to get the critical length. So let's calculate 1 over pi times 73, 115.2, square this guy. Okay, so this is in kpsi, so everything works out. Let's see here. Okay, and we should get the result in inches. So AC is equal to 0.1278 inches. So this is the point. Up till this point, we will integrate it and get the results here. Okay, so but before we do that, now we have a certain critical length, 0.1278 inches. Let's go back to the slides and see. Probably we can, for this critical length, we can probably extract the properties of beta. So for 0.1278, let's go back here. We get the ratio first, A over B ratio. Okay. What is the B? B is the width. For our case, what is the width of the plate? 1/2 inch. By 0.5. Go back to the MATLAB. Let's say AC over 0.5 gives you 0.2556. Okay, so this is one ratio we may need, 0.2556. So somewhere this is 0.3, 0.2, so somewhere in between here. We also need H over B is half the length. Let's see here. We need the total length here, length of the specimen. Are we given any length? We are not given the length of the specimen. Let's see here. And also this is a bending moment load. Are we in the right graph? No, we are not in this graph. This is the graph we have to use. Yes, so this is a pure bending moment load. This is the graph we should use, A over H, and pure bending. This is the curve. So 0.2556 is halfway in between, and let's see, the value would be approximately here near 1.1. Let's see what they have assumed, a value of 1.1. That's what we get from the graph. 1.07. So they have assumed 1.07. We can assume the same value. Beta is equal to 1.07. And that's based upon this value. Again, let's calculate the critical crack length using the same formula. So remember, there is a beta factor here which is equal to 1 initially. So this beta will be going inside here, this part over here. So we need to calculate the critical length again based upon this. Beta value 1 over pi and 73 over beta 1.07 to 115.2. Okay, so what is the critical length now we get? Let's go here to MATLAB. Here we have to use 1.07 again. Okay. Get 0.1116. Critical length is 6 inches. Okay, so this is the critical length I will be using again. Remember that I have calculated the critical length twice depending upon the beta values. Okay. Okay, so now let's use the integral. The integral is 1 over c. We need all the values. And f is equal to 1 over c. What is the c value? Go back to the problem. And here. The capital C value is 3.8 into 10 power minus 11. The integral within the limits. The initial crack size is 0.004. And the AC is 0.1116. Use that value. And let's see here. Other values calculated. dA over beta times dA over beta is 1.07. Delta sigma, which is again we calculated delta sigma 115.2. And then root pi a. Okay, root pi is a constant, and a we have to integrate a power 1 over 2. Let's take all the constants outside and we
Doctor,
can
I think you
evaluate.
forgot the
Yes, sorry. So let's go here again. Beta delta sigma root pi a whole raised to the power m. No, should not forget m value. What is the m value here? Given 3 cube. Okay. So the cube value, and we can keep all the take all the constants outside and rewrite it. So let's simplify the constant part. Let's see. And this we're going to write constant because I want to calculate this part 1 by, so 10 power 11. We have 10 power minus 11. We can take it to the numerator. Divided by 3.8. Multiply that. And we have this quantity cube. So let's open this bracket and write it as cube. 1.07. Then 115.2. Multiply that by root pi. So pi raised to the power, we can write it as square root with a bracket. Anything else? No, that's it. So these are the constants, and we have raised it to the power 3. And we get 2.5234. Multiplied by 10 power 3. Here inside the integral, we have a power 3 over 2 in the denominator. So if you integrate it, what is the integral x power n? X power n plus 1 over n plus 1. So this is the relationship we are going to use. A power minus 3 over 2. So integrate it, you will get a power minus 3 over 2 plus 1. In the denominator, minus 3 over 2 plus 1 within the limits 4, and then we have 0.16. Okay. So what is the number of cycles to failure? Here we have minus 3 over 2 will give me, plus 1 will give me minus 1 over 2. And again we have a negative sign, minus 1 over 2. Okay, I can use the negative sign and reverse the limits here. 6 and 0.4. Reverse the limits. So in the denominator here, I have 1 minus 3 over 2 will give me minus 1 over 2. And the 2 will go to the denominator. Negative sign we have reversed already. So 2 times here. What we will have here, a power minus 1 over 2. So in other words, we can simply write it as 2 over square root of a. So if you calculate f based upon the constant multiplied by 2 multiplied by bracket open 2, we can take it outside, 1 over root a, so 1 over 0.004 minus should be square root because it is root a minus we have the critical length 1 over square root critical length, which is AC. Directly use the value, we get I think we use UNS. Okay, get 66492, whatever is the number of cycles to failure here. So 4 digits, 1 2 3 4, so 64,691 cycles, so 0.99. So we can write it as 2 here. Cycles to fail. Number of cycles to failure is this much, 64,000 some cycles. So let's see what is the value they have calculated. Similar, 64.7. 64, so thousands, around 7,000 cycles. Okay. So this is how we find the life of the specimen based upon the linear elastic fracture mechanics calculations. Okay. Now recall that we have not gone through what equations we must use in stress life method. In stress life method, we saw only one experimental result, and that experimental result is the SN diagram or the Wooler curve. Okay, again SN or Wooler curve, named after the guy, diagram or curve, whatever you want to call it. In the SN diagram for steels and other BCC specimen, We saw on the y-axis, we plot sigma amplitude we apply on the specimen, and on the x-axis, we have number of cycles to failure. And then for BCC specimen, there is a flattening out of the curve. And because experimentally we have proved there is an endurance limit, SE value, this is the property we are going to use for BCC materials. For FCC materials like aluminum, we saw that we do not have an endurance limit. At least experimentally, we can show that endurance limit doesn't exist. On the other hand, what we have is a fatigue limit at 10 power 7 cycles or 10 power 8 cycles or 1 million cycles, whatever it is. And then we use that value. Again, it is important to understand the difference between endurance limit or fatigue limit. It is also called fatigue limit, and fatigue strength of the aluminum. Fatigue strength for FCC like aluminum, and endurance is for BCC like steel. For example, steel has BCC structure. Okay. Endurance limit is the limit below which the material will have infinite life. On the other hand, fatigue strength does not have any property like that. Below fatigue strength, again, you will have only finite life. Okay. There is no infinite life for FCC materials like aluminum. So clearly you can see the advantage of using steel and materials like aluminum. Aluminum is lightweight, but again, it has finite life below fatigue strength value. However, steel, if you design your component in such a way that your stress lies below the endurance limit, then the component will have infinite life even under fatigue loads. But the disadvantage is you have very high density. Again, there is no theory behind why endurance limit exists for BCC materials and why it doesn't exist for FCC materials. There is no clear understanding here, and this is a potential research area. Again, fatigue modeling is quite complicated, and we do not have proper theories. You can say the theories, so-called theories, are based upon experimental observation, and it is more an empirical formula rather than a theory. Okay. All right. So we have about 5 minutes. I will introduce the stress life method here. Before we begin the stress life method, we have to see some of the properties of materials we will be using here. In most cases, endurance limit, if you are not able to obtain what is the endurance limit value, at least for the steel, various kinds of steels we are dealing with, there is an empirical relationship between the endurance limit and the tensile strength of steel. So according to experimental observations, what they have figured out is for various steels, various types of steels, you have carbon steels here, alloy steels, wrought irons, etc. If they plot the endurance limit versus the ultimate strength of the material, various types of steels, this is the relationship they get. There is a linear relationship between these two values up till a certain point, and after that it flattens out. There is no increase in the endurance limit, even though the ultimate strength of the material increases. Okay, so this is a very important property you need to realize. You can increase the strength, ultimate tensile strength of the material by doing any kind of material processing. Still, the endurance limit of the specimen reaches a maximum value and it flattens out for steel. So this is a general experimental observation. So as per this graph, we can get an empirical relationship between the endurance limit, experimental values of endurance limit, and the ultimate tensile strength of the material. So this gives that. And in your design, You will often use this empirical relationship to predict what will be the endurance limit of the material based upon the ultimate tensile strength of steel in particular. Do not use this empirical relationship for any other material except steel. Okay. Now, 0.5 times SUT is the value from 0 to, see here, you are given the graph here. Any value between 0 to 700 megapascals, or sorry, 1400 megapascals, you will use the relationship 0.5 times SUT for predicting the SE endurance limit of steel. So if your SUT value lies between 0 to 1400 megapascals, this is the relationship you will use to get SE value. On the other hand, if your SUT value is greater than 1400 megapascals, then you will simply take the endurance limit as 700 megapascal for steels. Okay, so this is the very first important property, and you should know how to get or predict the values from SUT values. Okay, let's skip here for a moment. If you recall the Coffin-Manson relationship from the strain life method, we are going to use very similar type of equations in the SN diagram. Okay, so what we are doing here, I will briefly explain it and then we can discuss the equations next class. I'm going to go back to the SN diagram here. In the SN diagram, we know that we have infinite life in this region. When your amplitude of stress is below the endurance limit for steel, you will have infinite life. So there is no need to predict what would be the life of the specimen. But imagine your amplitude of stress is above the value of the endurance limit, then you will have finite life. You cannot have infinite life, and you need to predict what is the life here. So let's assume this is the value of sigma A. Then we can draw a horizontal and then gives the intersection point, put a vertical, and then we will be able to figure out what is the life. To do this, we need the equation of this line between 10 power 3 cycles and 10 power 6 cycles. So we need a curve fit for this line. So usually there is a curve fit done between this limit and also between the limit 1 cycle and 10 power 3 cycles. So we need to come up with these equations, and we will come up with these equations similar to your strain number of cycles to failure graph in the same way. Let's go back to the slide. In the same way, we also obtain the relationship between the elastic strain and the curve in the same way. So basically, not the strain here, we have to replace this by stress. So using your Hooke's law, we can replace this by stress, which we will get by multiplying by the E values here. So take the E value here, multiply it to the left hand side, you will directly get what is the stress. Okay. So the equation, after combining this, the final equation we will get between the stress and number of cycles to failure is this equation, and we are going to use this equation to predict the number of cycles to failure. So here we have some constants. We need to know how to get the values of these constants, B, F, etc. So next class, I'm going to derive some equations to get the values. You will not be asked to derive any equations. We will use the final form of the curve fit to obtain the number of cycles to failure for a completely reversed loading. Okay. So if you don't have any other doubt, I'm going to stop right here and we will meet again on Tuesday. Okay. By the way, during your break, I'm going to give you a take-home quiz on the first 4 chapters so that it might help you in your test 1. Okay. Any doubts? If you do not have any doubt, I'm going to stop here. Let's meet again on Tuesday. See you guys.